Okay, so we will discuss some problems on chemical kinetics. The first problem is the decomposition of N2O5 can be written as 2N2O5 goes to 4NO2 plus O2. The concentration of N2O5 reduces from 2.86 molar to 2.39 molar in 150 minutes. Calculate the average rate of reaction and production rate of NO2 during this time. Okay, so the rate of reaction is minus half d concentration of N2O5 by dt. Okay, so we can write this one as minus half. For finite change, you can write change in concentration of N2O5 by change in time. So we write minus half. What is the change in concentration of N2O5? So it started with 2.86. This is initial concentration. This is final concentration. So final minus initial. So 2.39 minus 2.86. And what is the time here? Time here is 150 minute. So 150 minute. This is moles. So if we carry out this one, we get 1.56 times 10 to the minus 3 moles per minute. So this is the rate of reaction. Now next problem is the production rate of NO2. Okay, so the rate of production of NO2 so if we write this one as 1 by 4, the coefficient is 4 for NO2, so 1 by 4 d concentration of NO2 by dt. Again it will be a plus sign here because it is forming here. For finite change we can write 1 by 4 delta NO2 concentration of NO2 by delta T. So you get 1 by 4 times. Okay, now 2 moles of N2O5 gives 4 moles of NO2. So per N2O5 moles, okay, so gives you 2 times of NO2, right? So what is the change? Okay, change is your 1 by 4 times. Okay, so we write this one as basically we need to calculate delta NO2 by delta T is 4 times rate, right? The rate of formation is this, so we get 4 times rate, not 1 by 4, so you get 4 times rate. So we get 4 times 1.56 times 10 to the minus 3 moles minute inverse. So you get 6.24 times 10 to the minus 3 moles minute inverse. Next we move to problem number 2. It says N2O5 decomposes at 475 Kelvin like this. N2O5 goes to N2O4 plus half O2. If the initial pressure is 0.26 atmosphere and after 40 minutes the reaction of the total pressure of the gas mixture is 0.38 atmosphere, calculate the average rate of reaction in millimeter per minute inverse, atmosphere per minute inverse and moles per minute inverse. Okay, so we start with this. So let P is the answer is let P is the decrease in pressure of N2O5, decrease in the pressure of N2O5 in 40 minutes. Then write N2O5 gas gives to N2O4 gas plus half O2 gas. So, we started with 0.26 atmospheres, and then there was no N2O4 and no O2, right. So after T equals to 40 minutes, we get 0.26 minus P, because P is the decrease in pressure, right, atmosphere. So it goes to P, and this is P by half. Okay, so the total pressure after 40 minutes, total pressure after 40 minutes is 0.26 minus P plus P plus P by 2, and it shows that total pressure is nothing but 0.38 atmosphere. So it gives you, so this P get cancelled, so 0.26 plus P by 2. So we get P is 0.38 minus 0.26 times 2 atmosphere. So you get 0.24 atmosphere. So decrease in pressure in 40 minutes is 0. So the decrease in pressure in 40 minutes equals to 0.24 atmosphere, and so in 40 minutes the decrease in pressure is 0.24 atmosphere. So if we convert into millimeter of mercury, so 0.24 times 760 mm of Hg, right. Okay. So we get 182.4 mm of Hg. So average rate of reaction, first part is average rate of reaction. So we have to calculate in millimeter per minute. Okay, so this is in millimeter unit pressure, and minute is 40 minutes, right, divided by 40. So you get 4.56 millimeter minute inverse. So this is the first part of the problem. Now second part, we call atmosphere per minute. So atmosphere we already know. So again, average rate of reaction is 0.24 by 40. So this is atmosphere, this is minute. So we get 0.006 atmosphere minute inverse. Okay, and the third is moles per minute. Okay, so for that, so from ideal gas equation we know. So from ideal gas equation, we know PV is nRT. Okay, so we calculate N by V is P by RT. Okay. So we get N by V is P is 0.24 in atmosphere unit, R is 0.082 in liter atmosphere mole inverse K inverse, and T is 475 K. Okay, so if we calculate this one, so N by V, now you get moles per liter here. So you get moles per liter here. So the value of N by V you will get 0.0. N by V gives is 0.006 moles. 0.006 moles. This is the value of N by V. Okay, this is mole. So rate, so this change is happening at after 40 minutes, right? So, rate of the reaction is now, so rate of the reaction is 0.006 moles by 40 minutes, right, 40 minutes. So, you get 1.5 times 10 to the minus 4 moles per minute. This is very interesting problem. Now, we move to problem number 3. It says, for a reaction A plus 2B plus C goes to A2BC, rate of the reaction is found to be, rate equals to K times concentration of A times concentration of B times concentration of C, with a rate constant 3.4 times 10 to the minus 4 moles, mole to the minus 2 till L to the 2 is to the minus 1. What is the initial rate of reaction with concentration of A naught is 0.3 moles per liter, concentration of B naught is 0.4 moles per liter, and concentration of C naught is 0.64 moles per liter. Determine the rate of reaction when 0.045 moles per liter of A reacted. Okay, so rate. Okay, so if we start with the rate, so what is the rate? So rate is, as mentioned, rate is K concentration of A times concentration of B times concentration of C. This is the rate. Okay, and the value of K is given. Okay, so K is 3.4 times 10 to the minus 4 mole to the minus 2 L to the 2 S to the minus 1. If concentration of A naught is 0.3 moles per liter, okay, so concentration of B naught, because 2 times of A, so you get 0. Oh no, again given concentration of B naught is given 0.4 moles per liter, and concentration of C naught is also given 0.64 moles per liter. Okay. So rate will be K 3.4 times 10 to the minus 4 times 0.3 times 0.4, because K times concentration of A, concentration of B, and concentration of C, times 0.64. Okay, this is your mole liter inverse, second inverse. So if we do it, we get basically 2.6 times 10 to the minus 5 moles liter inverse, second inverse. This is the rate when initial concentrations are concentration of A naught is 0.3 moles per liter, concentration of B naught is 0.4 moles per liter, and concentration of C naught is 0.64 moles per liter. Okay, now from the reaction we can see, from the reaction is A plus 2B plus C. From the reaction we can see if 1 mole of A is consumed, then 2 moles of B and 1 mole of C will be consumed. Right? Okay. So remaining B the concentration of B. So initial concentration was 0.4, right? And 2 times, so this is the concentration of A reacted. So initial concentration of B is 0.4 minus 2 times this, since the concentration of when 1 mole of A reacts with 2 moles of B, so the remaining B will be 0.4 minus 2 times 0.045, right? That is your moles per liter. Moles per liter. So if we calculate this one, we get 0.31 moles per liter. Similarly, remaining concentration of C will be 0.4 minus 0.64 now, 0.64 minus so 1 mole of A, when 1 mole of A reacts with 1 mole of C, so 0.045 moles of A reacted, so 0.045 mole of C also is reacted, so minus 0.045. So this is your moles per liter. So if we do it, we get 0.595 moles liter to the minus 1. Okay. So the rate. So rate is K time concentration of A, concentration of B, and concentration of C. Now what is the concentration of A here? That we did not calculate. So remaining A basically. So this one is reacted. Okay. So remaining A we did not calculate. Okay. So remaining A we need to calculate. Remaining A, concentration of A is 0.3 minus 0.045 moles per liter. So if we calculate this one, we get 0.255 moles liter to the minus 1. So the rate, now we got all the values of concentration of we got the values of concentration of A, B, concentration of B, and concentration of C, and value of K we also know. So K is 3.4 times 10 to the minus 4 times concentration of A is 0.255 times concentration of B is 0.31 and concentration of C is 0.595. Okay, so if we carry out this one, we get basically 1.59 times 10 to the minus 5 moles liter to the minus 1 second to the minus 1. Next we move to problem number 4. It says ammonia decomposes as 2NH3 goes to N2 plus 3H2. The rate of reaction can be written as d concentration of NH3 by dt is minus K1 time concentration of NH3, and d concentration of N2 by dt is to K2 times concentration of NH3, and d concentration of H2 by dt is concentration of K3 times concentration of NH3. What will be the ratio of K1, K2 and K3? Okay. So the rate of the reaction, we write the rate of the reaction, is minus half, and then d concentration of NH3 by d2 by d2. So the coefficient is 2 here, so we get half here, and since NH3 is getting consumed, we get minus sign, okay, equals to d concentration of N2 by dt equals to 1 by 3 d concentration of H2 by dt, right. So 3 is the coefficient here, we get 3 in 1 by 3 here, and plus sign here for nitrogen and plus sign for hydrogen because they are producing here. Okay, so substituting with the given values, we write half of K1 times concentration of NH3, right, because it is given that d concentration of minus of d concentration of NH3 by dt gives you K1 times concentration of NH3. So, if you substitute it, we get this one equals to K2 concentration of NH3, and you get 1 by 3 K3 concentration of NH3. So, we get K1 by 2 equals to K2 equals to K3 by 2. Okay, so, if we multiply this whole thing with suppose 2, so we get 2 K1 equals to K1 equals to 2 K2 equals to K3, right. So, K1, so we can get K1 by K2 is twice by 1, and K2 by K3 is 1 by 2. Sorry, this is 3 is there, okay, not 2, this is 3. So, if it is 3, then we need to multiply everything by 6, okay. So, you get 6 K1, 3 K1, 3 K1 is 6 K2 and then K3, no 2 K3. So, you get K1 by K2, so you get basically 3 K1 equals to 6 K2. So, we get K1 by K2 is 6 by 3 is 2 by 1. Similarly, we get 3 K1 is 2 K3. So, we get K1 by K3 is 3 by 2, and 6 K2 equals to 2 K3. So, we get K2 by K3 is 2 by 6. Okay, so, we get K1 is to K2 is to K3 is 2 is to 1 is to 3, right. For problem number 5, it says the decomposition of SO2Cl2 at constant volume can be shown as SO2Cl2 goes to SO2 plus Cl2. This is first order reaction. It says the initial pressure of the reaction is 0.46 atmosphere, and after 200 seconds the pressure is 0.68 atmosphere. Calculate the rate of reaction when pressure of the mixture is 0.84 atmosphere. So, the reaction it says, okay, so for the decomposition of SO2Cl2, so for the decomposition of SO2Cl2, SO2Cl2 gas. Okay, so we get SO2Cl2 gas gives to SO2 gas plus Cl2 gas, right. When T is 0, initial the starting, so initial pressure, if we say this is 0.46 atmosphere, and this is 0 and this is 0. When T is 200 second, so when T is 200 second, so total pressure is 4.6, so total pressure is your 0.6 atmosphere. So, we need to consider that X amount is broken. So, 0.46 minus X atmosphere here. So, here you get X, there you get X. So, total pressure P equals to 0.68 atmosphere equals to 0.46 minus X plus X plus X. So, we get the value of we get the value of X. So, this gets cancelled, So x is 0.68 minus 0.46, so you get 0.22 atmosphere, right? 0.22 atmosphere. So this is the value of x. So calculate. So this calculate the rate of reaction when pressure of the mixture is 0.84 atmosphere. Okay. So basically what we need to get is so at time t, so at time t, so we can say when t is 200 second, when t is 200 second, so we write k, rate of the reaction k is 1 by t ln P naught by twice P naught minus Pt. So what is the value of P naught? P naught is the initial pressure, and Pt is the pressure at time t, right? Okay, so we get the value of k is 1 by 200 ln. Okay, so P naught initial pressure. Okay, initial pressure was 0.46 by twice P naught minus Pt. So 2 times 0.46 minus 0.68, right? So we get value of k is, if we calculate this one, we get the value of k. So the value of k is here is k is 3.2 times 10 to the minus 3 second inverse. Now if the total pressure is 0.84 atmosphere, then the pressure of SO2Cl2 is twice P naught minus Pt, right? That's what we got. So we get 2 times 0.48 minus 0.84. So you get 0.12 atmosphere. Okay. So rate of reaction when Pt is 0.84 atmosphere is rate is 3.2, this is a rate constant, 3.2 times 10 to the minus 3 second inverse, and then the value of pressure of SO2Cl2, because this first order reaction with respect to SO2Cl2. So we write 0.12 atmosphere. So we get 3.84 times 10 to the minus 4 atmosphere second inverse. So this was problem number 5. Next we go to problem number 6. For a reaction 2A goes to B plus C, following data were found. Okay, so it says that experiment 1 is different at different time, initial concentration of B, A and B are given. Determine the order of the reaction with respect to A and B and write down the rate law. Okay. So now so from the experiment actually you can write first we first consider R1. Okay, so say the rate law R1, rate constant R1 is K, concentration of A to the X, concentration of B to the Y, right? We consider this. Now B raised to the Y. Now for experiment 1, we write R1 is K 0.15 raised to the x and then 0.15 raised to the y, right. Similarly, for experiment 2, we write R2 is k 0.30 to the x times 0.15 to the y, and the rate here also given the value. This is your 2 times 10 to the minus 6, here 4 to the 10 to the minus 6, right. So, you see the rate is getting doubled when concentration of A is getting doubled here, keeping concentration of B constant. Okay. And for experiment 3, we get R3 is k concentration of 0.30 raised to the x times concentration of 0.45 raised to the y, and the value is given 1.2 times 10 to the minus 6. Now, if we compare experiment 1 and 3, we see that okay, when concentration of A is getting doubled and concentration of B is getting tripled, okay, 3 times, okay, here from experiment 1 to 3, the rate constant, the rate of the reaction becomes 6 times. So, now if we divide R1 by R2, so we get R1 by R2, we get R1 by R2 is 2 basically, or R2 by R1 or 1 by 2. If we consider R1 by R2, then we get 1 by 2. 1 by 2 is we get 1 by 0.15 in the numerator. In the numerator we have 0.15 raised to the x by 0.30 raised to the x. Okay, so we get basically x is 1, right. Similarly, for R2 and R3, R2 by R3, if we do, we get 1 by 3 is 0.15 raised to the y by 0.45 raised to the y. So, again we get y is equals to 1. Okay. So, the rate law. Okay. So, the order of the reaction is, first we have to calculate the order of the reaction. So, first part is the order of the total of the order of the reaction, total order of the reaction is 1 plus 1, so 2, and the order of the reaction is 1 with respect to both A and B. So, with respect to A, the order is 1, and with respect to B, the order is 1. So, if that is the case, the rate law is rate equals to k concentration of A raised to the 1, concentration of B raised to the 1. We should move to problem number 7. Okay, it says time needed for 25% completion of a first order reaction is 28 minutes. What will be the 75% and 90% completion time? Again, this is very simple problem. So, we know k for the first order reaction, k is 1 by T ln concentration of A naught by concentration of A, right. So, when 25% reaction gets completed, so k is 1 by, so the 25% reaction completed in 28 minutes, right. So, 1 by 28 ln. So, 25% reaction completed. Okay. So, if we consider A naught is 100, So 25% gets consumed, A is getting consumed, so we get this is 75, right? Okay, so we get K is 1 by 28 ln 4 by 3, right? So if we calculate this one, we get basically the value of rate constant is 1 times 10 to the minus 2 minute inverse. So this is the value of K. So value of K we have already got. Now we need to use this value of K for next two problems. Okay. So when let us consider 75% reaction will be completed in T 75 minutes. Okay, so we know K is 1 by T 75 is times ln. So we started with 100 and 75% completed, so concentration of A is 25. So we get T 75 is 1 by K ln 4. So you get T 75 is 136 minute. Now we consider 90% reaction will be completed in T 90 minutes. So we know K is 1 by, so K is 1 by T 90 times ln. So we started with 100 and then 90% gets completed, so we have left with 10. Okay, the concentration of A at time after 90% completion, concentration of A is 10. So we get T 90 is 1 by K ln 10. So if we carry out this one, we get T 90 is 230.3 minutes. So this was problem number 7. Next we move to problem number 8. It says the half-life of a radioactive decay, carbon 14 decay, is 5680 year. A wood contains 60% of carbon C. Estimate the age of the tree. Okay, so decay constant K. So we know that this is a first order kinetic. It follows first order kinetic, radioactive decay, right? So decay constant K is 0.693 by T half. T half is the half life. Okay. Now T half is, now value of T half is given. This T half is 5680 year. So 5680 years, right? So value of K is 0.693 by 5680 years. So we get 1.22 times 10 to the minus 4 year to the minus 1. So this is the value of rate constant. Now we need to calculate the age of the tree. Okay. So since the rate constant this is first order decay, so rate constant is proportional to the number of 14C atom in the sample. The sample means the tree, right here, the sample. So we can write T is 1 by K ln n naught by n. So if we calculate this one, we get 4187 years. Okay. Again for the first order reaction, okay. So this is the first order reaction. So it follows like that. Okay. So the age of the tree is 4187 years. Okay. So we had started with 100, then we have 60% carbon. Okay. So if we substitute those things here, N naught and N, we end up with this value 4187 years. And then problem number 9, it says prove that for a first order reaction, time taken for completion of 87.5% reaction is 3 times than the time taken for the completion of 50% reaction. So reaction is first order. So we know for first order reaction, K is 1 by T ln initial concentration of reactant and by the concentration of reactant at time t. Okay, so for when 87.5% reaction is completed, then concentration of A is if we say the concentration of A naught is 100, so this is 100 minus 87.5. Okay, and then we get 12.5. So K is 1 by T. If we say T1, okay, so we considering T1 and second is required for 87.5% completion of the reaction. So we get ln 100 by 12.5. Similarly, considering T2 second is required for 50% completion of the reaction. We write K is 1 by T2 ln 100 by 50. Okay, so if we divide, okay, from there we actually get T1 is 1 by K ln 100 by 12.8 gives you ln 8 basically. This is ln 8. And from here we get T2 is 1 by K ln 2. So we get T1 by T2 is ln 8 by ln 2. So ln 8 is ln 2 to the 3 by ln 2. So we get 3 ln 2 by ln 2. So we get 3. So T1 is 3 times T2, or it says that the time taken for the completion of 87.5% reaction is 3 times than the time taken for completion of 50% reaction. So hence it is proved. Okay. So next problem is the decomposition of nitramide can be written as NH4,2NO2 in aqueous gives N2O gas plus H2O liquid. If the half-life time for a first order decomposition of nitramide is 2.5 hour at 15 degrees Celsius, then they estimate the time required for 90% decomposition of nitramide. If 12.4 gram of nitamide is allowed to decompose, what will be the volume of N2O at this point at STP? Okay. First is the half-life time is given. Okay. So, this is first order reaction and half-life time is given. So, T half is given, T half is 2.5 hours. Okay. So, 2.5 hours means 2.5, so 150 minutes. So, 150 minutes. Now, for first order reaction, K is 0.693 by T half, that we know. So, 0.693 by 150, this is minute inverse. This is the value of K. Okay. So, again for first order reaction, we know K is 1 by T ln concentration of A naught by concentration of A. So, 90% decomposition of nitramide. So, the concentration of A is now 10 if we consider concentration of A naught is 100. So, we get T is 1 by K ln A naught by A. So, value of K we know that 0.693. So, 1 by 0.693 by 150 and ln A naught by this is 100 by 10. So, value of T we get 150 by 0.693 times ln 10. So, this is in minute. Okay. So, if we do it, basically we get T is value of T is 2.77 times 10 to the minus 1 hour inverse. This is the first part. Next part is, okay, so where if 12.4 gram of nitamide is allowed to decompose, what will be the volume of N2O5 at this point? Okay, so sorry, this is your value in minute, whatever the value is there. So, you calculate this one. So, you get the value of minute. Okay, so you get the value is T is you get 8.3 hours. Okay, this is the value of T you get. Okay. Now, next problem is what will be the if 12.4 gram of nitamide is allowed to decompose, what will be the volume of N2O at this point at STP. Okay. So, for the reaction, we can say we can say 1 mole of NH4 NH2NO2 NH2NO2 decomposes and produces one mole of N2O, right. So, reaction you see 1 mole NH2NO2 gives 1 mole of N2O. Okay, so, moles of NH4NO2. So, 12.4 gram of NH2NO2 means how many moles? So, 12.4 by 62. So, the molar mass of NH2NO2 is 62 grams. So, we get 0.2 moles, right. Okay, so, the moles of NH2NO2 decomposed, because 90% is decomposed is 0.2 times 90 by 100, right? Okay, so you get 0.18 moles. Okay, so it says that 0.18 moles, since 0.18 moles of NH2NO2 decompose, so 0.18 moles of N2O is produced, right? Okay, so N we have got. Okay, so 1 mole of, we know 1 mole of N2O gives or occupies 22.4 liter at STP, right? We know that. So 0.18 moles of N2O occupies 22.4 times 0.18 liter. So if we calculate this one, we get 4.03 liters at STP. Okay.